Good morning, good afternoon, or good evening, depending on where you are in the world. My name is Sharon Florentine. Welcome to today's Security Boulevard webinar, the Kubernetes Network Security Effect, brought to you by ARMO. We have an awesome webinar for you today, as usual, but before we get started, I do need to go over some quick housekeeping items with you. First of all, today's webinar is being recorded, so if you miss any or all of it, you can absolutely go back and watch it again. We'll be sending an email with a link to access the webinar on demand, or you can visit us at securityboulevard.com/webinars, and it will be there for you. We are taking questions from the audience too, so make sure to put your questions in the Q&A tab there on your webinar console, and Amir will be happy to answer those at the end of the presentation. We are also doing a drawing at the end for 4 $25 Amazon gift cards, so stick around and see if you are a winner. And I am pleased to formally introduce to you today Amir Kalshansky. He is the VP of Product at ARMO, and he's going to talk to you today about the evolution of network security policies and how to adapt those to a modern cloud-native infrastructure. Amir, welcome. Thank you so much. I'm going to put myself on mute and turn my camera off and let you get right into it.
Thank you very much, Sharon. So, as mentioned before, my name is Amir Kalshansky, and I'm the VP Product at ARMO. I have more than 15 years of experience in cybersecurity and product management. I did a couple of roles in Checkpoint and other companies. And now I'm leading the product at ARMO. And I'm doing network security for the past, 20 years or more. And network security is a subject, a topic which is close to my heart. So I really want you to enjoy this presentation as much as I did when I prepared it. So why are we talking about network security? Why is it relevant? And when we talk about network security, why is it needed? The reason is that in today's world, everything is connected. And we all know that software is vulnerable and attacks happen through the internet. That's the technical reason why we need network security and why network security is important. But other than that, it's required by many compliance frameworks. So we all need network security, and it's very important for all of us. Taking you back 20 years ago, I was a young person joining Checkpoint. At that time, it was the leading company for network security. We used to call it internet security. Back then, customers usually had the following architecture. They had their application sitting behind a firewall. And then I'm trying to so they had the application, it was sitting behind the firewall. They had the DMZ section where they had things like their mail server and file server. And they defined access according to the application requirements. And then the application owner came to the security operation team and told them, or network security team back then, and told them, our customers are coming from the US, so we need the US address space to be accessible to my application. My application is getting updates from Perl.com or packages from Perl.com, so I need to have access to from my application to Perl.com. And it's sending mails to my customers, so I need an access to the mail server, which sits in the DMZ. And then, and of course, the application changed once a year or twice a year, but the cadence of change was, very, very. It was once a year or twice a year, but not more than that. And then the security team created these objects in their firewall, placing names for every IP address that belongs to the entities that we just described. And they were creating firewall policy that says my book review app should go to pearl.com on port 80, please allow it, and install it on the main firewall. That was not enough because usually the application that sits behind the firewall needs some network address translation rules. So they also created network address translation rules like you see here. If my book review app goes to pearl.com in any service, oh, sorry about that. So if my application goes to pearl.com on any service, change the source to my external interface and keep the destination as original, and again do it on the main firewall. And once they did that, everything was in place. They did some tests. They saw that everything is fine and it's working perfectly. And that's it. They deployed the application, and they had to deal with it maybe once in a few months or maybe once a year. Now, what can go wrong? So one thing that can go wrong is changing the IP address, changing the application, changing the IP addresses of the external entities. It can really go wrong because they had to go back and change the IPs on the objects that they created. Changes in the ports and protocols. So let's say that I allowed HTTP, but now someone moves to HTTPS, so I need to change the ports and protocols. And in some cases, if I publish a new application, movie review instead of book review, and it resides on the same subnet, I need to do some adjustments to the policy and to the IP addresses, etc., in order to adjust to the new situation. Before I jump and describe the situation in Kubernetes, I want to kind of go fast on Kubernetes network security, Kubernetes networking, and how it works without security. And then we'll talk about how and why applying security is not a straightforward task. So in Kubernetes, basically, there is something which is called CNI. CNI, it's the container network interface that basically has the following responsibility. When a pod comes up, it goes to the Kubernetes goes to the CNI. It says, "Give me an IP address," and it gets an IP address, and then the CNI plumb the pod to the node and allows communication to the pod. There are two modes in Kubernetes: island mode, which is the default in some CNIs, and the second one is not an island mode, which is, as far as I remember, it's the default state in AWS using the AWS CNI. The idea with island mode is that the pods are sitting on a different subnet than the nodes. So it means that when the pod wants to communicate with another pod in a different cluster, in a different node, it does it by routing between the different nodes. When we talk about when one pod wants to access another pod, and since the pods are changing all the time, it's the Kubernetes scales up and down the system according to your definition and according to the required load. So in order for one pod to access another pod or access another service, it has to do that using a different type of entity than the pod IP address. So in order to do that, Kubernetes has a construct called service, and service can be of three types. Cluster IP, meaning that it's an internal IP address. It's like a virtual IP address that when pod A wants to contact pod B, it doesn't know the IP addresses of pod B, but it does know the IP addresses of the service that represents pod B. So it initiates a packet to service B, which will then route the traffic to the available pods according to the definition in Kubernetes. The second option is node port. The idea with node port is that Kubernetes assigns, this is a service that can be accessed from the outside, from the internet, and then Kubernetes assigns a port, usually high port, on the node, on the worker node in Kubernetes, and then there is an external entity that routes the traffic or load balance the traffic to the node port address, and then when it gets to the node port address, it will be routed according to the service definition to the relevant pods based on the current state of Kubernetes. I mean, if it has 1 pod or 10 pods, it doesn't really matter. The third entity is, or the third type is load balancer, and this is relevant to cloud. In cloud, you can create in Kubernetes a service which is defined as type load balancer, and then the cloud vendor knows to create an external load balancer, a network load balancer in some cases, that will get the traffic and will route it to the relevant pod which is associated to this service. Now, using load balancer created a situation where you have a lot of load balancers in your environment, which is, of course, annoying. And then Kubernetes created something which is called ingress. And the idea with ingress is kind of aggregating all the services. So basically, you can say /cart will go to the cart service, and checkout will go to the checkout service. And it's a logical aggregation, a layer 7 routing entity, if you think about it. But it created a situation where every pod, at the end of the day, is its own perimeter. And something which is very important to our discussion is that when you have 2 pods communicating one with the other, if you define in one pod that it can talk to the other pod, or as it being said in Kubernetes, you define one pod to egress to another pod, it doesn't mean that the other pod knows that it needs to get ingress traffic from the first pod. So when you do that, you need to do that on both sides. You need to set the ingress in one pod and the egress in the other pod in order for it to work, which is kind of confusing. The last thing you need to know is that basically in island mode, when a container 1 issues, or when pod 1 issues a connection to, let's say, ARMO.com, it will send the traffic. The traffic will be natted on the node, and then it will go out, and maybe it will be natted again on your cloud or on your on-prem network. But if you place an appliance, a firewall, a next generation firewall of any kind outside of your cluster, it means that you will see the node IP. So when it goes to armo.com, maybe you don't really care. But when it will go to evil.com, and you will see traffic goes from your node to evil.com, one of the questions you might ask yourself which pod initiated this traffic? It's a very, very important question. And this is a very, very dynamic environment. So in order to answer that, you need to sit in the cluster, maybe where I'm pointing here, in the CNI before NAT is being done. Because if you're sitting outside of the cluster, you will not be able to answer this very important question. So why is legacy security not the right answer in Kubernetes? Other than the obvious things that I just mentioned, the Kubernetes environment is immutable. Since it's immutable, it changes all the time. Your application now is no longer a monolith. It's broken to small microservices that communicate and have different communication requirements. And they are immutable. So every piece of this software can change at its own pace and time, and you can't really control it. And as we saw from CNCF reports, more than 30% of the organizations today say that they have a daily change in their Kubernetes environment. And that's a lot. So we moved from once or twice a year in a situation where you can really ask yourself what are the communication patterns, and you can anticipate it and wait for it and plan it, to a hectic situation where everything is constantly changing, and you need to kind of run and try to understand what's going on. But talking with a lot of customers during the past few years and asking them, what do you need? What are your requirements when it comes to network security in Kubernetes? So most of them are doing the north-south hygiene using WAFs and firewall and next-generation firewalls, etc. But they're looking for east-west microsegmentation. And this is the most important requirement that comes from many discussions with a lot of customers. Most of the customers, they prefer connectivity over security. So if it works, great. If it works and it is secure, fantastic. But if it doesn't work because of security, I'm not going to use it. And then it has to come all the challenges, of the constantly changing environment, being able to understand which pod created the traffic, etc. So I try to kind of describe the process of creating a policy as we did in the old days, as I showed you before. And let's try to see what is the recipe for creating a good network security policy. So the first part is to map the communication patterns, to understand how the resources are talking with each other, what are the requirements, the ingress and egress requirement of each one, what are the ports, what are the protocols. Then you need to create a policy. Hopefully you have a language to describe this policy. Then you run the application and you hope that everything is working well. And if it's not, you need to find what's not working well and you need to fix it. And once you did that, you need to start again. Maybe something changed. Maybe you didn't test all the scenarios and you have this once in a month billing process that comes up and needs access to the external world or something like that. And once you finish it, you think you're good to go. And in Kubernetes, something changes. But we will get to that eventually. So if we look at Kubernetes, Kubernetes has a built-in network security construct, which is great. It's called network policy. And you can see that it's very, very similar to the network firewall rule that I showed you at the beginning of this webinar. It has a pod selection section, which is basically the install on. It's the, as I mentioned before, at the beginning, the firewall created my perimeter definition. Here, the pod selection is creating my perimeter definition. So it says where I need to install this policy. And then I have a set of rules. So here I'm highlighting an egress rule saying that if these pods wants to access this address range on this port, they can do it. There are some problems with Kubernetes network security. There are some high-level problems like who is enforcing the policy. Not all CNIs enforce policy. Not all of them enforce policy in the same manner. So it's a little bit different, and there are a lot of CNI plugins like Calico. It's the most famous one, but there are others like Flannel and Cilium and others. The good thing about them is that they're label-based. So if something changes, but as long as they keep the same label, they will get the same policy. They are declarative, so it's easy to declare what you want. It's allow only, so you define only the connections or the communication patterns that are allowed by the pod. The problem with this construct that it doesn't have any logs, so you can't really know if something is bad or good because you don't have any ability to understand which rule is being enforced, which policy is being used, why a packet is being dropped or accepted, etc. You don't have a drop and block options, which sometimes for some customers it's very important. Like customers would like to block update, apt update for a certain pod. Doing it in Kubernetes using this construct is challenging. And right now there is no FQDN support. So basically, if you want to say, I want my pod to go to ARMO.com, I can't really do that because it's not supported in this construct. So let's see how it works and why it fails. Okay, so I have my application, the book review application, and it went into I broke the monolith, and now it's modern application using cloud native technologies. You can see that I'm no longer using Python, Perl, I'm using Python, and I'm no longer using my DMZ mail server. I'm using a SaaS mail service. And I mapped all the communication patterns, and I created this amazing policy in day one, and I published my application, and I know that it's working, and I'm completely sure that it will keep working. But then at day two, someone changed the communication patterns. Maybe because a new version is going to come. A new version came because we are rolling out some major thing or capability that requires this change. And now, although the policy is based on labels, now my east-west traffic changed. So the policy is no longer relevant. Now I need to map it again. Okay, so I was able to map it. And then after a few hours, someone did the full version rollout, and they released this new AI service that goes on my data and does something amazing. And now I understand why the communication channels or patterns changed. But still it doesn't work. And by now I probably removed my network policy, and I just kept my north-south hygiene and kept the east-west open. So the problem was that I don't have a way to visually map the communication between the different pods or microservices. I have a construct to create a policy, which is nice. I can't really run the application and watch how and see how everything works. And then the last thing, it's really, really hard to debug if something is not working. So that's why it doesn't work in Kubernetes. Other than that, there are two problems, general problems in Kubernetes. And I'm going to describe them. The first one is that when you created the policy saying that your a cloud or web tier can talk to your DB, you really wanted to say that your Nginx process can talk to your SQL process. You didn't mean that the malware that lands on your Nginx pod can communicate also with your SQL. And that's a fundamental problem in Kubernetes, as well as any cloud construct. Can be a VM, a pod, a container. It's the same challenge. Another thing that you need to know is that most of the east-west traffic is clear. By default, Kubernetes is a flat network, meaning that every pod can talk to every other pod. If it's in the same namespace, if it's in a different namespace, they can still communicate, and all the traffic is clear. So if an attacker lands on your and gets access to your host, he can just run a simple TCP dump and just collect all the data and decode it quite easily. And now I know that 90% of the people think, hey, but there is Istio. Oh, sorry, before that. And if you think that it will never happen, actually a year ago, researchers found that there is a vulnerability in Kubernetes allowing someone that enters your cluster and has the ability to create services, to create a rogue service and then route your traffic to the rogue service. And since the traffic is probably not encrypted, you can intercept it and decode it and understand it. And this issue was not solved. There is some workaround or suggestion in version 21, but it didn't really solve this problem. And now let's get back to Istio. So some of you might say, hey, but Istio actually solved this problem, because Istio creates a mutual TLS communication between my different pods, and then an attacker cannot really understand what's going on there. So Istio didn't solve the identity issue. When I'm saying identity issue, I mean that if an attacker lands in service A by hacking something in service A, the attacker can communicate with service B because it's allowed by Istio, and it gets the inherent identity of the proxy, of the sidecar proxy that Istio adds to each service. So it doesn't really solve the identity issue. It does solve the clear east-west traffic. So now the traffic is fully encrypted using mutual TLS, which is great. It didn't change the policy language. So for layer 3, it's the same policy language. It just adds a layer 7 policy language. If you install Kiali, you get visualization. So you are able to visualize the communication patterns between different services, but it has complexity and latency, which is something that I heard from a lot of customers. And if you follow the CNCF reports, you still see that there is a low adoption rate when it comes to Istio or any other service mesh. So that's not a real answer to our challenge. Okay, so what do we want, or what would I suggest people, users, to do when it comes to network security in Kubernetes? So one important thing is to enforce zero trust. Since we know that each pod is its own perimeter, and there are a lot of pods in every environment, we do want to be able to enforce zero trust. And to you that doesn't really know what's zero trust, the idea with zero trust is don't trust, always verify. And it's really based on the identity of entities. And when it comes to the real world, it's something you know and something you have. And that's how we know that when we use our iPhone and the iPhone recognizes us and gives us access to different application or our Gmail account or whatever, we know that it's strongly authenticate ourselves, because it's something that we own, like our mobile device, and something that we know, like a password or a token or a secret or something like that. But when it comes to microservices, it comes to something that you have, and in Kubernetes, it's the service account. Each pod can identify itself and allow access or not using an identifier that if an attacker enters to the same perimeter, he can use the same identifier to identify himself as a legitimate actor in your Kubernetes cluster. The second thing is a mutual TLS. I would definitely prefer that the traffic will not be clear. There are in most of the clusters, you have different namespaces, and I really don't want people from my dev namespace to be able to enter my prod namespace and then run TCP dump and kind of see whatever goes there. So a mutual TLS is definitely something that I would recommend someone doing. The third thing is to be able to visualize the network. It's very important to understand your communication patterns. It's very important to understand what you're protecting against. And I always say that visualization, maybe it's not security, but you cannot protect what you cannot see. So visualization is very important in order to create a better security. And then you need to apply a policy, to have a policy construct or a policy settings or capability that can meet these rapid changes. If 30% of organizations today have a daily change, imagine what will be in a year, 2 years, 5 years from now. Definitely, it will not stay 30%. It will only grow. So what we do at ARMO and how we solve this challenge. As I mentioned before, identity is very important for zero trust, and that's the secret sauce of our technology. What we do, we look at pods, we look at the memory footprint of each pod, at the processes that are running, at the libraries that are being loaded into memory. We calculate and create a very strong identity. This identity is something that you cannot forge, you cannot pass it to a different microservice. It is the identity of the microservice. And then in runtime, when the pod is running, then we escort the pod in runtime, and we make sure that no one changes the integrity of this pod. And this technique, it enables us also to create a mutual TLS between different entities in your environment. Basically, it is a perfect zero trust solution because it's tying the identity, the integrity of the workload. So if a workload is compromised, if we identify that someone entered a malicious code into the application, we immediately take it out of the equation. It will not be able to communicate, or the malicious part will not be able to communicate. And then by that, we are creating a perfect zero trust environment. So now let's run the same example as I showed before and how it works in ARMO. So what we do, we create a policy, a very simple policy. We call it a basic zero trust policy. And as you can see here, the only thing we said here that the source is the namespace dev and the destination is the namespace dev. And basically it tells our guards, our ARMO guards, that as long as the workload is not compromised, and as long as its integrity is perfect, it can communicate with different parts, with different ARMO guards or with different pods. That's the only policy that you should create using ARMO. The second thing I get is visualization of all the traffic patterns. Who talks to whom? Who initiates the traffic? What is the port? What is the service? Whether it is encrypted or not, I can see it visually, and I understand that. And in case a new pod is being scheduled, as long as it has the ARMO guard in it, it can communicate freely. So I don't really care now that the communication patterns has changed, as long as they have ARMO guard and everything is not compromised, and the policy says that everyone in the namespace can communicate freely. The new pod can communicate freely. The communication patterns that changed can change and still work. And that's how we solve this rapid change challenge. A side bonus is that we also solve the problem, since we use the identity, we also solve the problem that if a malicious code enters your pod and tries to communicate, we will not allow to communicate with one of the other pods. We will not allow it as it doesn't have the identity and the integrity requires to create this communication channel. Okay, so let's see now how it works. We are able to map the communication channel patterns. You can use it in staging or testing, and we will be able to show you a map of all the communication patterns of your application. Then creating a policy is quite simple. You can create a basic zero trust policy, or you can create a policy that really expresses all the communication channels that you visualized in the first stage. Then you can run the application and see that it is working. We do have logs, and we can show you if something is being dropped, why it is being dropped. If something is being accepted, we can show you why it was accepted. And then you can fix it and come back. So we give you all the ecosystem to create an east-west a network policy that will be facing or handling all the challenges that Kubernetes has placed on us. So I want to conclude this session, and I created this table kind of to wrap everything that I mentioned before, and I'm comparing here Kubernetes, Istio, in the ARMO, and I'm doing Istio and not any other service mesh just because Istio is the most popular service mesh, but it can be any other service mesh. And when we look at the actions, Kubernetes native is allow only. It doesn't have a deny or log capabilities in native Kubernetes. Some CNIs do offer that in their enterprise edition version. Kubernetes Istio has an allow and deny, but it's for the sidecar and it's based on identity. It's not a layer 3 microsegmentation. And in ARMO, you have allow, block, and alert. The cool thing about ARMO is that we have a mode that says that you can put the policy in alert mode, meaning that we will not block the communication. We will create an alert saying, hey, we should have blocked this packet, but you're running in alert mode, so we didn't block it. And then it helps you to create this healthy policy that you want. Encryption is not available in native Kubernetes. It is available in Istio between the different sidecars. And in ARMO, it is available, but it's doing it between the actual processes that we mapped that are running in your pod before it was deployed. Network visibility is not available in native Kubernetes. It is available in Istio using Kiali, and I don't know how it is done in other service meshes. And in ARMO, we do have the ability to show you the network connectivity, as well as a clear TCP dump is available on demand. So if you have any challenge and you want to debug your situation, you can create on-demand TCP dump that will give you a clear copy of the traffic. Logging capabilities is not available in native Kubernetes. It is available in Istio, and it's also available in ARMO. And the zero trust policy notion that I just mentioned and explained is not available in native Kubernetes nor in any service mesh, but it is available in ARMO. And that's where I think we have a huge advantage over the other solutions. So thank you very much for attending. I hope it was interesting. And I really hope that you're going to apply network security in your Kubernetes clusters. Thank you.
Awesome. Thank you so much, Amir. So we do have a couple questions here, and I know you just kind of touched on this, but I'm going to ask again. How are there, you mentioned Istio, but this works pretty much the same with other service meshes like Linkerd or Kuma or anything like that?
I used Istio as a comparison, not other service meshes, because I think that Istio is, according to CNCF, Istio is the most popular service mesh, and I thought it will be a good comparison. I didn't want to go to any specific service mesh like Linkerd or any other in order to run this comparison.
Okay. And does anything change with the new Kubernetes update?
Yeah, that's a really good question, because in Kubernetes 21, there are new constructs for that eventually will replace ingress. These constructs they are doing something similar to a service mesh when it comes to a canary deployment. So imagine that now you will have this object in Kubernetes, a native object in Kubernetes, that you will be able in Kubernetes to say, I want 90% of my traffic to go to this pod, to the blue version and 10% to go to the red version, and then you can kind of play with it. So this sets the canary deployment in Istio or any other service mesh to be kind of redundant. And then the second thing, if you add ARMO on top of your environment, you get the mutual TLS benefits of Istio. And I didn't talk about it and I didn't elaborate on it, but maybe there is a question coming on this topic. But one of the benefits of using ARMO over Istio, for example, is that in Istio you need to set all the certificate authority and the assignment and revocation of all the certificates, and it's a huge headache. In ARMO, we do it on our own. We assign the certificate to the processes. We have a patent around how to secure the certificate or any other secret, even if they are stored in memory. So we know that attackers, when they land in your pod context, they will probably drop the memory and get all the secrets from there. We have a technology to overcome that, and again the certificates and all the CA is built into the solution, which makes it really easy to onboard and manage.
Gotcha. Okay. So I think following on to that, Charlotte has a question about whether ARMO can be used as a replacement for service mesh or just an augmentation.
So I think I answered that in right now. I think that it will not, I think that once the gateway construct will be used, or it will become available and not an alpha construct in version 21, it will be more mature and it will be part of the infrastructure. Then using ARMO, you can get the service mesh benefits without the cost associated, which is latency and the overhead of managing the entire solution. So I really hope that in, version 30 of Kubernetes, you will use ARMO as well as a native Kubernetes capabilities, and you will gain the same benefits as you get from service mesh.
Okay, thank you. Francesco wants to know if there's a way to automatically test the correctness of those policies.
You mean the correctness of the policies that are created in ARMO?
I'm not sure. Francesco, can you elaborate exactly? We'll move on real quick while he.
Okay.
Yeah. Does ARMO work with Google Anthos?
Yes. We work with since we run in the context of a pod. As long as we can understand the we understand the pod itself, we can run there. So we didn't have any problem with Google. Actually, we are doing all our demos, and the demo that I created in the past webinar are based on GKE. So we didn't encounter any problem. We also support OpenShift and other container orchestration platforms.
All right. Well, let's see. I think that about does it for us today. I'm sorry. Francesco has added some clarification here. So we'll get to this, and then I can wrap up. He says,
okay, yes. Yeah, I'm reading it. Yes, yep. Check policies defined among several services with the business logic of the application. Basically, what we do is we are able to check that policies are not overlapping. So we check that that indeed the policy matches what the user wants to describe, and then if there is a conflict, we alert on a conflict. We do generate a lot of data on the communication patterns of the application, giving the user the ability to kind of understand what are these communication patterns, we enrich the traffic with the service and other Kubernetes constructs. So it's really, really easy to understand what are these communication patterns. And as I mentioned before, we have the basic policy that you can use to create a very, very simple and robust policy. But if you want, we have the ability also to kind of, if you think about it, we plot these communication patterns between the different parts. You can create a policy out of it by clicking a button. We can make it an implicit policy that defines the different communication patterns. Although I think that using the basic policy, you can get the same thing with a very, very simple, in a very, very simple way.
Awesome. All right. So thank you all so much for attending and for sending your questions in. Just a reminder, if you missed any or all of the presentation today, it has been recorded, so you'll be able to go back and watch it again. Let's see. Now it is time to select our Amazon gift card winners. All right. So our first winner today is Logan A. Congratulations, Logan. Next, we have Ron L. Congratulations, Ron. Third winner is Wilson M. Wilson, congratulations. And finally, David A. Congratulations to all our Amazon gift card winners. We will be sending an email with a link to show you how to access those. So keep an eye on your inbox. And if you don't see it, check your spam folders.
Sharon, why I never win?
I know, me either, Amir. We got to put our names in, I think, a couple more times.
Okay, good.
Maybe next time.
Great.
All right, cool. Also, if you did have a question for Amir that we did not get to today, rest assured we will be sending all of those questions over, and he will be able to follow up with you afterwards. All right, that about does it for us today. Thank you so much again for your time, and that's it for me. I'm Sharon Florentine signing off.
Bye.